Okay. Okay. Good afternoon, all. In previous few lectures, we have discussed related to the heat treatment of the steels, and in that we have completed various heat treatment processes, like heat treatment processes used for the steels, like annealing, normalizing, and hardening, tempering. After that, we have discussed related to the surface heat treatment processes. Uh, in that, we have learned carburizing, nitriding, carbonitriding, and flame hardening, induction hardening. And after completing these processes, there is the one more concept that is the hardenability that we are going to discuss in today's session. What is the meaning of hardenability? Then, for checking that hardenability, we are going to conduct a few tests. From that, we are going to discuss related to the Jominy and Quench test. And there is one more test that is Grossman's method is there, which is very much similar to the Jominy and Quench test. Just slight changes are there that we are going to discuss here. This Jominy and Quench test is also included in your practicals. Uh, we are going to conduct one practical on this. Whichever practical procedure is that we are going to conduct in the lab, that we will discuss here only. Okay. In this lecture, we are going to discuss the concept of hardenability, then Jominy and Quench tests, how it is performed, then what are the outputs from this tests at the end that we are going to discuss in brief. Then what are the factors affecting the hardenability that we are going to discuss at the end of this test. And the last method is that Grossman's hardenability test. Just the one change is there as compared to Jominy and Quench test. Remaining procedure is very much similar that we will discuss in the later half of this lecture. Okay, first we will start with this. What is the meaning of the hardenability? From that we will start. Okay, now we will start this session. What is the meaning of hardenability? Now, hardenability means the ease with which a steel piece can be hardened. Okay, means in simple words, how we can means whichever depth of hardening is obtained. If suppose particular steel component is given, and how you are going to do obtain the desired depth of hardening, or how that material will provide you the desired depth of hardening, that can be termed as its hardenability. Means capacity or capability of producing the desired depth of hardening of that particular steel component or that steel sample or steel piece is termed as the hardenability. Now here, while performing the means while checking the hardening, here we are going to check the hardening which is obtained by transformation of austenite to the martensite phase. Okay, that we are going to consider here. While checking the hardenability, we are going to check that whether that particular steel component will produce or give the desired depth of hardening by martensitic transformation. That particularly martensitic transformation is very important, because some steels may show the increased hardness or improved hardness due to formation of bainite or pearlite also, but that we are not going to consider that. It is very necessary that austenite should get transformed to martensite only. That type of hardening we are going to consider here. And the ace with which that steel component can be hardened to the by the martensitic transformation, or how easily a particular steel material or steel component can be hardened by giving the martensite at the end. Okay, martensite will be there, and that is termed as the hardenability of that particular steel. Means depending on their hardenability nature, you can classify them as uh, non-hardenable steel. Suppose low carbon steel is there, then these low carbon steels, you are directly saying that these are non-hardenable steels, because we cannot perform hardening on it. cannot perform the hardening process on it. Then medium carbon steels and high carbon steels, you are terming them as, or they are known as hardenable steels. Medium carbon steels, high carbon steels, or alloy steels. These are hardenable steels. And then how we are going to decide it? Then for that we are going to decide the depth of the hardening. You can see the second point. We are going to check how much depth of hardening can be produced under the given cooling conditions. Depending on that only, we are deciding whether that material or that steel component is hardenable or it is a non-hardenable steel. Okay. Now, how to evaluate the hardenability means whether it is hardenable or non-hardenable. For that, we are going to take the two methods, or simply it is evaluated by these two methods. Here I have highlighted by point 1 and point 2, by determining the minimum cooling rate. Okay. Here you have to decide the minimum cooling rate, transform the austenite steel to the martensite. Okay, simply we are going to decide, simply we are going to heat that steel material from room temperature to above, you can say that A1 or A3 temperature, depending on the type of the steel. So you can say that A3 or ACM temperature. Either you have to choose above A3 or above ACM, depending on the type of the steel, whether it is hypoeutectoid or it is hypereutectoid steel. And above that, it will be in the austenite phase. Okay, that steel sample which is heated above that A3 or ACM temperature, that is termed as austenitized steel. Okay, and from that you are cooling it to the room temperature and you are getting the martensite structure. Okay, and to achieve this, whichever minimum cooling rate is required, that you have to determine. And depending on that minimum cooling rate, you have to decide whether that cooling, if that cooling rate is achievable. Okay, whichever minimum cooling rate is there to transform austenite phase to the martensite phase, if that cooling rate is practically possible, then you can say that that particular type of steel is hardenable. Okay, that particular steel is hardenable or it is having higher hardenability. So this is the first point, means by determining the minimum cooling rate to transform the austenite phase to the martensite phase, you can decide whether that steel is hardenable or it is a non-hardenable steel. If whichever minimum cooling rate is required to transform that austenite phase to the martensite phase is not practically not possible, that steel will be termed as non-hardenable steel. For example, you can say that low carbon steels, in case of low carbon steels, the minimum cooling rate required to transform austenite phase to the martensite phase is not possible. It is means you have to do very rapid cooling, and it is practically almost impossible to achieve that much faster cooling. Hence, the low carbon steels are termed as the non-hardenable steels. Okay, this is the first method. Then the second method is determining the thickness of the largest section that can be converted to same structure. Okay, same structure means from austenite to the martensite. But here in the first case, what we have done, we have determined the minimum cooling rate. Okay, minimum cooling rate to transform the austenitized steel to the martensitic structure. Now the same structural transformation will be there, from austenite phase to the martensite phase. But instead of determining the minimum cooling rate required, here we are going to determine the thickness of the whichever steel sample we are using here, the largest thickness we are going to decide, or determining the largest thickness to get the same kind of the structure from, means transformation from austenite to the martensite under the given cooling conditions. We are going to check the largest possible thickness in which we can transform austenite phase to the martensite phase. Okay, in these two ways, means what is important, transformation should occur here in such a way that means from higher temperature range from austenite we are getting we are cooling it to the room temperature to get the martensite. Okay, initial stage is heating that steel component, and we are terming it as austenitized steel. Okay, or this is the process of austenitizing, means heating the steel from room temperature to above A3 temperature or above ACM temperature, and only austenite phase will be there. And from that austenite phase, we are cooling that steel sample to the room temperature, and we are transforming it to the martensite. And if to achieve this transformation, okay, to achieve this transformation, the minimum cooling rate to achieve this transformation is practically possible, then that kind of steel will be termed as hardenable steel. And if that cooling rate is not possible to achieve in your practical life, then that type of steels are termed as non-hardenable steels. Okay, uh, that in by using or taking this reference, we have classified low carbon steel as non-hardenable, and medium carbon steel, high carbon steel, and alloy steels, these are all hardenable steels. Okay, or they shows very high hardenability. Then the second method to determine the hardenability of a steel component is you have to determine the largest thickness of that steel section in which you can achieve the same transformation. That is, you are transforming austenite phase to the martensite phase by using the given cooling conditions in, and you will get the martensite at the end. And you have to determine here the thickness. Okay, how much thickness, possibility of means maximum thickness where you can get the same transformation. Okay, determining that thickness will also help you to determine the hardenability of that steel component. Okay, then these are the two methods of determining the hardenability. The After seeing this hardenability, now to determine the hardenability of a particular steel component, if suppose particular steel component is provided to you and they have asked you to measure its hardenability, then there are certain tests you have to perform on it to determine its hardenability. And from that test, the one very popular test, or the test which will give you the better result, is Jominy and Quench test to determine or to measure the hardenability of the given steel component. Jominy and Quench test is used. Now here, these are the whichever write-up I have provided here. This is for your reference, you can read it. Means I will explain this slide with the help of the diagram. In this, I have explained the points added are related to before determining the hardenability of that particular steel sample. For conducting this Jominy and Quench test, you have to prepare standard specimen. Okay, whichever steel material is given to you, that from that steel component you have to prepare one specimen with standard dimensions, and that dimensions I have mentioned here. Now whichever steel sample, suppose one steel sample is provided and they have asked you to determine its hardenability, whether it is hardenable or it is non-hardenable. Then what you have to do, first you have to convert that steel component in the desired shape and size, means you have to transform that to the standard specimen. And now here you have to take the cylindrical shaped specimen. You can read this, or I will show you the diagrams. This type specimen you have to prepare. Okay, this is the schematic representation of the specimen used for Jominy and Quench test. Now I will explain how the specimen is prepared. You have to take the steel sample, or you have to prepare the specimen of that steel in such a way that its diameter is 1 inch. Okay, diameter is 1 inch, its length is 4 inch. Okay, 4 inch length, diameter 1 inch, 4 inch length. Then at the one end of that specimen, at the one end of the specimen, you have to Means it's machined shoulders you have to prepare there to provide proper support while performing the actual tests. Okay, at the one end you have to prepare shoulders. Okay, shoulders are prepared. You can say that these are the machine shoulders at the one end, so that this specimen can be properly adjusted while performing the test. Then after this, after preparing this standard specimen, what you have to do, you have to take this test specimen. This is also termed as Jominy's specimen or Jominy's test specimen. This specimen you have to take and you have to do the heating in the furnace. Now, this component is heated in the furnace above, either you have to choose A3 or ACM temperature. Okay, above that you have to heat it, whichever steel, depending on the type of that steel, you have to heat it above A3 temperature or above ACM temperature, so that there will be only austenite phase, and you have to provide sufficient holding time or soaking time, so that there will be uniform heating and only austenite phase will be there. This type of steel is termed as austenitized steel. Okay, you are heating it, and now while performing this heating process, you should take proper care that there should not be any decarburization. Okay, as temperature is higher, there may be possibility of some decarburization means loss of carbon element. Okay, loss of carbon. Now, how to avoid this decarburization? Now, while performing this heating process, you have to take care that whichever steel sample is there, that sample you have to keep in a steel container or steel tube, which is surrounded with the cast iron chips, and inside that you have to keep this specimen. While performing the heating, you have to take one steel tube. Inside that you have to place your specimen, and it should be surrounded by the cast iron chips, so that at the higher temperature ranges there should not be any loss of carbon, that is decarburization should not occur. This care you have to take while performing the heating. And here you have to provide sufficient holding time, so that uniform heating will occur, equal heating or equalization of temperature will take place, and only austenite phase will be there. This will be termed as, this kind of steel will be termed as austenitized steel. Okay, and after that you have to take this sample. Okay, after heating, and this heating process will be conducted in the furnace, and from that furnace, now you have to remove this sample and you have to take this sample. Okay, now you have to take this sample, and there will be one arrangement. This type of arrangement will be there. This is the Jominy and Quench tester is there. This equipment is available in our lab also. When I will show you that instrument also. Just what you have to understand here, I will repeat this procedure in the practicals also. Just try to understand this. This is now our specimen. This type of arrangement will be there. One picture will be there. You can say that where you can fix this specimen, and here one drum is there, and one pipe arrangement will be there, and from this pipe arrangement, uh, some water supply or water spray will be there. Okay, and now whichever heated sample or austenitized steel is there, that you have to fix in this picture, and from the bottom. Okay, from the bottom of that steel sample, you have to start the cooling. Okay, water will just flow from the bottom, or it will just be applied at the bottom surface. Okay, now here this pressure of the water is adjusted in such a way that when there is no specimen, the height of water is approximately 2.5 inch. Okay, how to adjust the pressure of water? Before keeping the specimen here, when free flow of water is available, that free height of the water is approximately 2.5 inch. Then the diameter, this inside diameter of this pipe from which water is coming out, that inside diameter is half inch, and distance between the specimen and this water pipe, it is also half inch. This is also mentioned here. Diameter of this pipe is half inch, and distance between the bottom end of the specimen and that pipe surface is also half inch. And when the specimen is not available, the free height of this water is approximately 2.5 inch. All these points I have mentioned here. Okay, all these whichever points I have discussed here, that I have written here that points, you can go through it. Just with the reference of this diagram, you can write that also. Okay, now one more thing is there, that is temperature of this water should be in the range 21 degrees Celsius to 27 degrees Celsius. Then after, okay, now after heating the sample, you are uh, removing it from the furnace. Now the steel sample is in the austenitized phase, or only austenite phase is there. Now that steel sample you will have to fix in this way, as shown in this diagram, and water flow you have to start. Then this water will means it will come in contact at the bottom end of the steel sample, and quenching of the steel sample will start. Now the end which is in directly contact with water, it will get quenched or cooled with very rapid rate, and the other end which is not directly in contact with water, here air cooling will take place. Okay, air cooling will occur, means it will get cooled in very much similar way to the normalizing process. Okay, this one end which is directly in contact with water, it will get means it is very much similar to the hardening process, and the another end it will get subjected to the air cooling. Hence the very much similar process will occur like the normalizing. Okay, now after providing now this process you have to continue for approximately 20 minutes. Okay, after 20 minutes you have to remove the specimen. Okay, this cooling process, this continuously this water will fall on the one end, this is the bottom end of the given specimen. Now after 20 minutes you have to remove this specimen now. Okay, now this specimen you have to remove, and after removing that specimen, now you have to measure the hardness. Okay, now you have to measure the hardness by taking intervals of 1 by 16th inch, or you can say that 1.6 millimeter distance from the quenched end. Okay, now this specimen you have to remove it after the cooling. That you can see here, this is your specimen, and you have to measure the hardness. This end is your quenched end. Quenched end means the end which, while performing the cooling, which is in directly contact with the water, this end is your quenched end. From this end, now you have to take the distance. Okay, you have to take the distance 1 by 16th inch distance, and you have to take the readings, approximately 10-15 readings you have to take. Okay, approximately 10-12 readings will be there, that readings you have to take, and you have to plot a curve. On y-axis hardness will be there, and on x-axis distance from the quenched end is taken, and a curve is obtained. Okay, this type of curve is obtained. This curve is termed as Jominy's hardenability curve. Okay, that curve I have also shown in this diagram. This is Jominy's hardenability curve. Jomany's hardenability curve. Okay, how this curve is obtained? The hardness is measured at intervals of 1.6 millimeter or 1 by 16th inch distance from quenched end. Already I have explained this. And hardness values are plotted as a, you can say that as a function of distance from the quenched end. And the curve which is obtained, this type of curve is obtained. This curve is termed as Jomany's hardenability curve. Okay, this curve you have to plot. Okay, so in this way, this Jomany's end quench test is performed. This is the schematic arrangement for that performance of the test. This is the specimen preparation. You can say that specimen preparation, schematic arrangement, and this diagram is you have to check the hardness by taking the interval means starting at the quenched end from quenched end by taking the distance intervals of 1.6 millimeter or 1 by 16 inch. You have to measure the hardness and you have to plot that hardness against the distance from the quenched end, and you will get a curve. This type of curve will be termed as the Jominy's hardenability curve. Now here, the end which came in direct contact with water, at that end you will find that the hardness values are more. Okay, at this end where we have means faster cooling, we are able to obtain the faster cooling. At that end, we will get the martensite phase. Due to that martensite phase, means austenite is transformed to the martensite at this end due to rapid cooling. Hence, hardness is very high. Okay, and as we are moving from this quenched end to the normal cooled or air cooled end, you will find that hardness values will be less and less, because due to this air cooling at the end means this austenite will get transformed to pearlite instead of transforming to martensite. To give the better hardness, it will get transformed to pearlite. Hence, here hardness values will be very less. Okay, so in this way this test is performed and its outputs are taken. Now what are the factors? Now here are certain factors are there which will affect the hardenability. Okay, hardenability of the steel. Now before going for these factors of hardenability of steel, first we will discuss this is the Jominy curves or Jominy hardenability curves obtained for different kind of the steels. Okay, depending on these curves only you can say that whether that particular type of steel is hardenable or non-hardenable. The first curve, okay, this is the first curve is for high carbon alloy steels. Then second curve is for high carbon, you can say that plain steels or simply high carbon steels. These are high carbon alloy steels, means carbon percentage will be very high and some alloying elements will be there. The second curve is for only high carbon plain steels, means no alloying other alloying elements are there. And this third curve is for low carbon steels, low carbon plain steels. Okay, this type of curve we will get. Okay, here you can compare it very easily. Depending on this curve, you can say that hardness, you are not able to improve the hardness at the quenched end also. Its hardness is almost constant throughout that specimen length. Hence, these low carbon steels are non-hardenable steels. And here we are getting some improved hardness at the quenched end. If you compare the first curve and second curve, some improved hardness, we are able to achieve the more hardness at the quenched end. Hence, you can say that these are hardenable steels. But if you compare now curve 1 and 2, whenever more alloying elements are there, its hardenability is more. Hardenability is more in the sense we will achieve the better hardness or more hardness values. And better hardness values, and it should be achieved, means we will be able to achieve it with more length from that quenched ends. Okay, you can say that from this quenched end, it is giving you the more hardness values, higher hardness values throughout the longer distance, or you can say that for the longer length of that specimen, you are getting more or higher hardness values when carbon percentage is high and other alloying elements are also present. Okay, this is the differentiation between high carbon alloy steels and high carbon plain carbon steels. And if there are only low carbon steels, these are non-hardenable. Okay, and from high carbon steels, If high carbon steel is with alloying elements, they will be having more hardenability. Okay, this is the description for this diagram. Now we'll move towards this point now. Factors affecting the hardenability. Okay, now some points I have highlighted here. Now hardenability of the steel. Hardenability of steel is directly related to the critical cooling rate. Okay, critical cooling rate that we have already discussed at the start only. Critical cooling rate means cooling rate which just bypasses the nose of the IT diagram. For this I will show you that slide so that you will able to understand the critical cooling rate. Okay, this is the critical cooling rate. Okay, the cooling rate which just bypasses the nose of the IT diagram. Now hardenability will depend on its critical cooling rate, or you can say that the distance of these nodes. Okay, this is the node of IT diagram, isothermal transformation diagram. Nodes, this is the nodes point, nodes of the IT diagram, distance of the nodes from the y-axis. Okay, when this distance is very less. Okay, as this distance is very less means you can say that very high critical cooling rate is required, means you have to cool that steel very rapidly to transform austenite to the martensite. Then hardenability is very less. Okay, this case is there in the low carbon steel. Critical cooling rate is very high. Okay, critical cooling rate is very high means you have to cool it very rapidly to get the martensite. That's why their hardenability is very less. And if critical cooling rate is very, you can say that very low. Critical cooling rate is low means it will move towards this side. Okay, means with slow cooling also you will able to get the martensite phase. That's why in that case hardenability of that steel will be very high, and such cases are there for high carbon steels, or you can say that high carbon alloy steels. Their critical cooling rate is very low, means with the slow cooling also you can achieve, or you will be able to transform austenite phase to the martensite phase. Hence their hardenability is very high. Okay, so this is the factor, that is the critical cooling rate. Depending on the critical cooling rate, whenever this critical cooling rate is very low, hardenability will be, you can say that very critical cooling rate is very low means with slow cooling also you will be able to transform austenite to the martensite. Hence hardenability will be more. And when this critical cooling rate is very high means you have to do very rapid cooling, then it is almost impossible in some cases to achieve that faster cooling. Hence that steel will may be termed as non-hardenable, or hardenability will be very less. Then second factor is the percentage of the carbon. Whenever high percentage of carbon is there, then what will happen? It will decrease the critical cooling rate. When high percentage of carbon is there, it will decrease the critical cooling rate. It decreases the critical cooling rate means it will improve the hardenability. The same will occur in case of increase in the alloying element. Whenever there is increase in the carbon and increase in the alloying element, it will decrease the critical cooling rate, and due to decrease in the critical cooling rate, its hardenability of that particular steel will get increased. Okay, the next factor is, I have explained this, there's carbon percentage, alloying elements. Now from this carbon and alloying element, the alloying elements are more effective to increase the hardenability. Okay, then carbon alloying elements will improve the hardenability more significantly, or these are more effective. The next point is the grain size of austenite. Whenever coarse grains austenites are present, okay, whenever coarse grain austenite is there, then that coarse grain austenite will provide you better hardenability. Why they will provide you better hardenability? As coarse grained austenites is there, means larger sized grains are there, it increases the grain boundary, it increases the grain boundary, and due to increasing the grain boundary, it will reduce the cooling rate, critical cooling rate. Due to increasing the grain boundaries, critical cooling rate will get reduced, and due to that it will improve, or it will provide the better hardenability. Then inhomogeneous austenite, if austenite is inhomogeneous, then it will show you less hardenability. And if some carbides, nitrides, borides, or some other inclusions, means impurities are present in the austenite, then it will reduce its hardenability, or that particular steel's hardenability will get reduced due to presence of these carbides, nitrides, or borides, or some other impurities. So these are some factors which will affect the hardenability of the steel. So in this way, this Jominy and Quench test is completed. What you have to explain in this Jominy and Quench test? First, you have to explain what is the meaning of hardenability in one sentence. You can write one or two sentence. Then whenever there is question, like suppose they will ask you Jominy and Quench test, or they will ask you the hardenability concept, you have to write the same description. If suppose they have asked you the Jominy and Quench test also, first you have to start with what is the meaning of hardenability, because this test we are using for determination of the hardenability of the steels. Then you have to first explain hardenability concept, then you have to explain the specimen preparation, then you have to draw these diagrams, then this arrangement you have to show, and you have to write the test procedure, and then you have to draw this diagram, that is the output, or you can directly go for this diagram also, variation of the hardness. Okay, then you have to explain how this curve is obtained, or what is the meaning of this Jominy hardenability curve. Then uh, after that you can draw this point, the different Jominy hardenability curves for different kind of the steels, or low carbon steels, high carbon steels, and high carbon alloy steels. Then you have to explain the factors affecting the hardenability of the steel, and you can draw this diagram also. Okay, this diagram is indicating that with the increasing the percentage of the carbon, critical cooling rate decreases, and as critical cooling rate decreases, hardenability will automatically increase. Okay, so this is the Jominy's end quench test, and the at the end some points are there. That is, this is one equation. This equation is used. This J is nothing but the Jominy's hardness, and this is the unit for that hardness values, whichever that suppose they will use for measuring the hardness. If they have used a Rockwell hardness tester, then this kind of units they are using. HRC is nothing but the unit for that hardness value. Now, why this equation I have written here? Sometimes, if you are aware about the composition of the steel, okay, if composition of the steel is known, then with the help of this equation, if all elements are known to you, you can put that values here, and the S is nothing but the distance in mm from the quenched end that you can take here, and approximate value of the hardness is determined. Now, without conducting the experiment, this approximate value can be determined. And why this is determined? With the help of this, you can choose the proper grades of the steels depending on the composition only, without performing the actual test, you can determine the approximate hardness value with the help of their compositions or elements present in that with help of this equation. Okay, and you can choose the proper grades of the steels for the depending on their hardenability, or depending on your use you can select the steel depending on only their composition. With help of this equation, if composition of the particular steels is known, you can put that values here, and approximate value of hardness can be determined. And if approximate hardness value is known to you, you can determine their hardenability values. Okay, so this is the Jominy and Quench test for determination of the hardenability. And one more test is there, that is Grossman's hardenability test. Now this is just for your information purpose. They are not going to ask you any questions here. Now here, what is the difference? Now in Jominy's and Quench test, we have selected only one specimen or prepared only one specimen. But in this Grossman's hardenability test, we are going to prepare number of specimens of the same steel material provided. We are going to prepare number of steel specimens with different diameter and different lengths. Okay, different diameter and different lengths, and we are going to repeat the same procedure, that is heating that steel sample and completing its means transforming it to the homogeneous austenite, that is austenitized steel, and then cooling it in the same kind of arrangement from the at the one end will be fixed. Now just the same process is repeated by preparing different specimens with different diameter and different lengths. Just while changing the diameter, you have to take care that whichever length you are going to select for that specimen, it should be 5 times the diameter. Okay, length of the test pieces is kept 5 times the diameter. And there is slight change while measuring the hardness values here. After the heating and quenching process, that sample one by one samples are selected, and exactly from the center we will cut that sample, and we will examine whichever cross section will be obtained after cutting the sample at the center. And that microstructure we are going to examine here. Instead of checking their hardness values, here we are going to check their microstructure. And the particular sample which will provide you the microstructure, which consists of 50% martensite and 50% perlite, that sample will be termed as, or you can say that that will be the critical diameter. That will be the critical diameter. And from that we can understand the how much depth of hardening can be obtained with that given steel sample, that is determined here. Okay, number of samples with different diameters and different lengths were taken, and here the diameter, depending on diameter, length has to be taken, and length generally is five taken 5 times the diameter of that steel sample. And all these samples are heated in a furnace above A3 or above ACM temperature, so that that steel will get austenitized. And after that it will removed and it will be quenched. And after the quenching process, the one by one sample is selected, and they are cut at the center, and their cross section is checked for their microstructure present. And the sample where 50% martensite and 50% perlite is present, on that particular sample, and the related diameter will be termed as the critical diameter. And depending on that, we are just going to decide the how much depth of hardening can be obtained for that steel samples. Okay, so this part is little bit difficult to understand without actual practical, so that we are going to perform the one practical test when the lab is available with us. At that time we will perform this practical, so that you will understand this Jominy and Quench test and how we are going to decide the hardenability For that, we have to conduct one practicals. We'll conduct that. Just I think in this session you have to try to understand uh, the procedure of this test and what we are going to do and what will be the outcome of that test and how to determine whether that steel is hardenable or non-hardenable. Okay, this much part is only there. So in this way, this heat treatment of steel chapter is completed now. If you are having any query, you can ask me. I will explain it. Or if you have understood all parts, please mention that in the chat box. Please give me reply. If any query is there, you can put that in the chat box. Or if all points are clear, you can also mention that in the chat box. Okay. Okay, in this way, our this don't leave the meeting first. I will stop this recording. Okay. Okay, in this way, this heat treatment of steel chapter is completed. Okay, approximately. Okay, this is the okay. One more slide I have added here. I will explain it. This slide is nothing but just I have summarized the surface hardening heat treatment processes which we have used, and that is by changing the composition of steel, carburizing, nitriding, and carbonitriding. Their subtypes. Carburizing is classified as solid, liquid, and gas carburizing. Nitriding is classified liquid nitriding and gas nitriding. And carbonitriding, depending on the medium used, is classified in liquid and gas carbonitriding. And without changing the composition of the steels, okay, flame hardening, induction hardening, and four types of flame hardening: flame hardening, progressive flame, spinning flame, and progressive spinning or combination flame hardening. This is just for your reference. Already we have discussed all these processes. Okay. In this way, this chapter is completed. Heat treatment of these steels. Thank you for attending all these sessions. We'll stop here. Stop.